Hello for the last and final lecture in our Physics 100 class. Although first I'll pose a question to you. If a video is recorded and uploaded and nobody watches it, does it truly exist? Alright, so, philosophy aside, our goal for this last lecture is to understand light itself. We only have one real equation today, and I just tell you what the constants are. Our objectives, we're going to learn about the properties of light, we're going to learn about diffraction, polarization, and finally how to create our very own holograms. Because holograms are cool. Bow ties, not a perspective, but holograms, cool. I know, that was so 2014. Just like with other waves, light waves have properties such as wavelength and period and frequency and amplitude. The first three we find the same ways we found other waves. Wave speed equals frequency times wavelength. The period is how many waves I get per second. The frequency is how many, period is how many seconds per wave. Frequency is how many waves per second. But for the amplitude, we have a very special way to calculate the amplitude. For light, the amplitude is measured by its energy. And the energy of light wave is equal to a constant h. This is the Boltzmann constant. It's like 6 times 10 to the minus 34th. You can look it up. It'll be on the OR. You won't have to memorize it. It'll be on the equation sheet for the test. You won't have to memorize it. Times c, where c is, if I haven't told you already, hopefully you've figured it out by now. C is the speed of light. That's our symbol for the speed of light, which is 3 times 10 to the 8 meters per second. Divided by this funny thing here, which is, let me spell that out for you, because this is a 100 class, wavelength. Now, it turns out it also equals the funny constant h, let's write that bigger, times your frequency. So if you have frequency, you use this equation, energy equals the constant times frequency. If you have wavelength, it's h times the speed of light divided by wavelength. In a vacuum, the speed of light is the speed of light. The wave speed is the speed of light. And energy. Right. Now, light behaves as both a wave and a particle. It's the weird duality of light. The particle of light is called a photon. So a photon, imagine I drew a wave on the board. This is my photon. This is my particle of light. And this particle can move in any direction, although in this case the way I've drawn it would have to move that way. Now, light has momentum. It's affected by gravity just like normal matter, which means that gravity is really attraction of energies, not an attraction of masses, but that's a bit beyond the scope of this class. Now, light spreads out. If an object is emitting light, even if it emits only one photon, that light spreads out as the distance squared. And so when you collect, the amount of energy you collect is going to depend upon your distance from the object squared. And it doesn't matter what obstructions you might encounter, it will take the easiest path to you as if the light knew what the easiest path was. It has to do with quantum mechanics. It's really complicated stuff. Basically, it says that the photon goes in every direction at the same time, even if it's one photon. And so you have an infinite number of realities. And then once that photon gets absorbed in one of those realities, all the other realities go away. And the reality where it got absorbed is the one that was always the one it was in. So it'd be kind of like asking every member of the opposite sex out on a date until you get married, and that was the person you were dating the whole time, and nobody else. No, really. Okay, not the best example, but you get the idea. It's really weird stuff when you get to quantum mechanics and Schrodinger's cat and stuff like that. But this leads us to certain properties of light, such as diffraction. So diffraction is when light behaves as a wave, not a particle, but a wave. Imagine I have a slit. that has two little peepholes in it, and light can travel into either one of those peepholes. Now, this peephole and this peephole are going to act like a source of light, and that light is going to spread out from both of those peepholes. And then if I put a screen over here, what will happen is the light will travel to that point in the screen from the two different locations. And so I have two pieces of light hitting the screen at the same time, but, and here's the kicker, did I just turn into a poker teacher? The kicker? Okay. The kicker is these two light rays have traveled different distances and are therefore in different phases. And so what you get on the screen is going to be determined by the phase difference between those two photons of light. And this is going to create what's called a diffraction pattern. Now, in the exact center of the screen, the distance that each light ray travels is the same. So my difference in distances, delta L, so this would be L1 and L2. Delta equals L2 minus L1. So we'll lose this so far. Here, delta L equals 0. Now, anytime we have a difference in 0, that means the phases are different by 0. And so what happens is they're in phase, and you get a bright spot. So this is a bright spot. This is the central bright spot. Now, what happens after that is that as you go in both directions, delta L increases. Delta L gets bigger. Now, as delta L gets bigger, we're going to see a pattern. Because when light adds in phase, it gets brighter. When light adds out of phase, it gets dimmer. And so, when we reach a point where it's out of phase, we'll have a dark spot. When it's in phase, we'll get a bright spot. Now, what determines whether it's out of phase or in phase? Well, if delta L is an integer number of wavelengths, it's in phase. If it's an integer plus or minus a half, not meaning plus or minus half a meter, but an integer plus or minus a half of wavelengths. So, half a wavelength, 1.5 wavelengths, 2.5 wavelengths, then you get a dark spot. And so what happens is you get a pattern of bright, dark, bright, dark, bright, dark, bright, dark. And so this is the first order dark spot, the first order bright, second order bright spot, etc., etc. There's a whole bunch of equations for it if you're in a higher level physics class, but I'm not going to get to those. You'll have to look those up in the next book. So this was first discovered about 200 years ago by Thomas Young, who passed light through two parallel slits like this, and he saw this kind of a pattern. This is called a diffraction pattern. And the advantage of a diffraction pattern is that the shape of this, if you have a two-dimensional slit, not just two slits, but you can make some three-dimensional object, it will reflect in the shape and size of this. And so you can actually get some understanding of very, very small things by passing light through and looking at the diffraction pattern, and you can figure out what that object actually looks like, even though it's too small to be able to see. Alright, so quick concept question. The wavelength of light is 600 nanometers. Nanometers is 10 to the minus 9th, but we'll just stay in nanometers for now. What is the path length difference, my delta L, for the first dark region? The first dark region, this region right here. Now, by delta L, I don't mean the distance from the center on the screen. That's going to be different than delta L. There's ways to calculate it, but we're not going to do that in this class. All right, but we're going to look at, just conceptually, the path length difference by delta L, meaning if I take this distance minus this distance, actually, yeah, that would be one distance. What is my value going to be? Is it going to be 0 nanometers, 300 nanometers, 600 nanometers, 900 nanometers, or 1200 nanometers? The correct answer is not 0, so we can eliminate that. It's also not 1500, which we can eliminate because I didn't write on the board. The correct answer, it has to be half a wavelength will be the first one. The second dark region will be 1.5. And then the third one will be 2.5, etc. So this is bright, because it's an integer number, it's 0 waves. This one's half a wave, so this one's dark. So this is the first dark one. The answer is 300 nanometers. And then 600 would be the next bright spot. And so this one's the central bright spot, so this would be the basically one wavelength, so this would be first order. I think I called it second order before, but it's actually first order because it's, if you do n times lambda, where the integer times the wave number of times the length of the wave, this is 1 lambda, so that's first order. N minus a half is for the dark spots. So 1 minus a half is a half. So 300 is the first order dark spot. And then this would be the second order dark, second order bright, etc., etc. You end up with bright, dark, bright, dark, bright, dark. Because of interference. The same interference we learned about a month ago is the same interference that causes the refraction pattern. Yeah, there was a reason why we learned about it. I know you're hoping that there wasn't, but there was. Sorry. Polarization. Now, when light comes at you, the angle it comes at you, or the angle at which this photon is, imagine I put this photon on a piece of paper. So my photon's drawn on my hand. I'm not going to actually draw it because that would be crazy. It can come at any angles it's coming towards you. As it's coming this way. It could be this way, it could be this way, it could be this way, etc. If it comes in randomly, if its orientation comes in randomly, we call that unpolarized light. Unpolarized light. But if some fraction of them above random comes in at some angle, we call that polarized light. And the percentage at that angle is the percentage of polarized light. So it can be 100% polarized or 10% polarized or whatever. 10% polarized means it's 10% this way and 90% random. Kind of like you take a multiple choice test and you know 10% of the questions and you randomly guess them the other 90%, you would be 10% polarized. Okay, bad example. Now, there are some ways to polarize light. If it's forced into some plane, it becomes polarized. One way to do this is through reflection. I'm not going to give equations about that. There is equations for that. I will be covering that. There are two types of polarizations, linear and circular. Linear means it's all polarized in the same line. Circular means it shifts like this in a nice linear fashion. I'm not going to talk much about circular polarization. That's too complex for this particular class. Not for you, the students, just for the class. And the percentage is percentage polarization. Now, polarizers allow us to weed out unpolarized light, or some fraction of it. So, think of a mailbox when you think of a polarizer. Mailboxes usually have some sort of slit, and if I put a letter like this, it goes in. If I try to put in a letter like this, it doesn't go in. It gets absorbed by the wall, bounces off the wall. If I put it at an angle, well, it cuts off the top, and I get some of that, but not all of it. And so polarizers allow you to beat out the random light, or at least a fraction of it, or are there ways instead of polarize to get rid of all unpolarized light? And a lot of like sunglasses and windshields are polarized because reflected light off of your hood, which create glare is usually polarized, and so you can get rid of glare by just adding a polarizer into your windshield. The polarizer is pointed perpendicular to the direction of polarization of the light coming off the windshield, and then it absorbs all of it. All right, and that's all I'm going to talk about polarizers. Holograms. All right, so how many of you own a hologram? Come on now, raise your hands. In fact, all of you should be raising your hands right now. Now, I know you think you don't own a hologram. You do. All right, how many of you have a debit or credit card? That should be all of you. I want you to reach into your wallet or purse right now, like I am doing. And I want you to pull out your credit card. All right. I'm going to do this the way you don't get to see my number. Okay. That would be bad. Posting that on YouTube. Oh. Okay, so I'm going to cover up my stuff and my stuff. On the back of my MasterCard here, there's this funny little earth that if I rotate it, it looks kind of 3D. That's a hologram. Yay, I have a hologram. If I pull out a Visa card, there is this funny little bird. I don't know how well you can see that, probably not very well. That's a hologram. And Discover has their own hologram. So, you all own your own hologram. Huzzah. All right. Now, holograms look three-dimensional when you rotate them, and if you walk by them, because they look like they have physical shape, even though it's flat and it's two-dimensional. So why do holograms look three-dimensional? And how do we create them? It turns out it's not as hard as you think. It has to do with diffraction. Again, it comes back to interference of light. So, in order to create your own hologram, the tough part is you need a beam splicer. Because you need light to interfere with itself. So you take the object that you want to turn into a hologram. My stick person. I don't know why I want a stick person hologram, but for some reason I do. All right, so I've got my stick person. Why did I draw a stick person? Because that's the only thing I could draw that doesn't come out in some weird way. Remember I tried to draw a fish and it came out as a tooth? Okay. Do I need to say anything more? No? Good. Okay, so I take a laser beam and I split the beam. Half of it reflects off the person, and I'm going to draw it non-realistically. And half of it just goes straight to my detector. Okay. Now, these two beams of light are going to interfere with each other. And that interference is going to cause the 3D illusion, because as I have a different distance from my image, I'm going to see something slightly different because of the diffraction pattern. And from that, I end up with my hologram. So that's how you get a hologram. All you need is a beam splitter and a cheap laser will do. You don't need anything fancy. And heck, you could probably just use a digital camera to do it too. You don't even need film. Hooray, 21st century. All right, so to wrap up for this semester, we've learned about the properties of light. We've learned what we can do with light, diffraction, polarization, and holograms. We, of course, will have a review, and then the final exam. Hopefully you've enjoyed the semester. Hopefully you enjoyed my lecture series. If not, post comments about what I can do to make it better. I'm sure there's a few things I could do to make it better. Some of which I could actually do, and some which probably not so much. But enjoy your future careers, and hopefully they will be better because of this series. At least that is my goal. And hopefully I've achieved that. Goodbye.